This is the second lecture for Anatomy and Physiology 132, the online class. Just like the first lecture, we're going to only hit the highlights in the lecture. So if there's something on this slide that's self-explanatory or that you can get just from reading the book, I'll probably just skip over it or won't mention a lot about it. So this is the Chemistry of Life chapter. And with Chemistry of Life, it's important to understand how chemistry works for anatomy and physiology so that you can understand how disease processes work. So when the body's chemistry goes bad, it's usually going to lead to some sort of disease. And a lot of this stuff should be reviewed. So for example, we're going to start here with matter. Matter is something you were talking about since second grade. So matter is anything that takes up space. So it has mass, it's made of things, and that's the definition for matter. Elements are the smallest types of matter in that, and one element is only made up of one type of atom. And atoms are the smallest particles of any element, and they can't be broken down by chemical means into anything else. So atoms are the smallest parts of an element. Okay, structure of matter. For our bodies, we have things called bulk elements, and our body needs these in large amounts. So those are things like carbon, oxygen, hydrogen. We also have on there, we can add nitrogen, phosphorus, potassium. Phosphorus isn't with an H. Potassium, trying to think of the other one. Oh, sulfur. Then there are things called trace elements that we only need small amounts of. So iron is one of these. Fe is iron. Iodine is another one. And then ultra trace elements, arsenic is something that we don't need a lot of. Okay, atomic structure. This is what one atom would look like. And an atom has an area that has a nucleus. Okay, atom has an area that has a nucleus. So this would be where the nucleus is. And the nucleus has protons in it. Protons are positively charged, and they are abbreviated lowercase p with a superscript plus. And the neutrons are in there. Protons and neutrons are both in the nucleus. Electrons are found outside of the nucleus. They're found in these energy shells, but they're not in this nice fixed pattern. They're found in these orbitals that go beyond the scope of this class. Okay, so for our purposes, we want to know that neutrons and protons are found in the nucleus. Electrons are found outside of the nucleus. Neutrons weigh 1 AMU. Okay, and AMU stands for atomic mass unit. It's just a unit of measurement that we made up, like all other units of measurement, to be able to discuss how much an atom weighs. Protons also weigh 1 AMU. Electrons, we say, weigh 0 AMU, and that's because electrons are so small that their mass really doesn't matter. Okay? Electrons are negatively charged, Protons are positively charged, neutrons are neutral. They don't have a charge. Okay, atomic number. Atomic number is equal to the number of protons in an atom. Okay, number of protons. So for example, if you look at a periodic table, you can see that carbon atomic number is 6. So it has 6 protons. Atomic weight is how much one atom weighs. And atomic weight is really the average of all the isotopes of the atom, but of the atoms in the elements. But we haven't talked about isotopes yet. But it's really atomic weight is equal to the number of protons plus the number of neutrons. Okay, so for example, carbon's atomic weight is 12.011 AMU. So there are 6 protons in carbon because we know that it weighs, or its atomic number is 6. So therefore, if there's 6 protons, there has to be 6 neutrons in carbon. Okay. So to get the number of neutrons, you can subtract the number of protons from the atomic weight. So this little bit left over here, the 0.011, is really because carbon has different isotopes. There's carbon 12, which is the most abundant type, carbon 13 and carbon 14. So this is the average weight of all 3 of those that we would find in living things. Okay. Isotopes. Isotopes are atoms of an element that have the same number of protons but different numbers of neutrons. Okay. So for example, carbon, we have our natural carbon. We have carbon 13, and carbon 13 has 6 protons, just like regular carbon, but then it has 7 neutrons. Carbon 14 has 6 protons because it's carbon and 8 neutrons. These isotopes occur naturally and they break down at a known rate, and that known rate is a half-life. Okay. So they break down at a known rate called a half-life. Carbon, say 14, breaks down, its half-life is 5,720 years, approximately. That means it takes 5,720 years for half of the isotope to break down. So let's say, as an example, we started with 100 grams of carbon 14, which we're just doing this for illustrative purposes. After 5,720 years, so one half-life, we'd have 50 grams of carbon 14. Okay, and then after another 5,720 years, we'd have 25 grams of carbon 14. So the half-life is just how long it takes to break down. Radioactive isotopes are unstable and they release a lot of energy until they're stable. And sometimes we use these to detect disease and treat diseases. So for cancer. We use radiation therapy. And then we can also use it to find tumors. Okay, so here's an example of science to technology, one of these little boxes in there. And since our thyroid gland is the only part of our body that uses iodine metabolically, we can use radioactive iodine to attack a thyroid tumor. And the purpose of the radiation is really to mutate the DNA within that tumor. So the radiation will go in, it'll cause a mutation in the DNA of the cancer cells and hopefully stop those cancer cells from spreading. And then when we talk about radiation, we can talk about alpha, beta, gamma particles. And these are all types of radiation that form from the breakdown of an isotope. So say, for example, plutonium. And the problem with the radiation is it passes through material. Some of these particles can't pass through, say, clothing. But then as you get smaller and smaller and more energy, these particles, like gamma radiation, can pass through your skin, and it can cause damage to your body. Okay, I'm going to talk about molecules. Molecules are formed when you have two or more atoms that combine. So you can have two hydrogens combine to form a molecule, or a carbon and four hydrogens can get together and form a molecule called methane. Compounds are when you have two or more atoms of different elements combining chemically. So really the methane is more of a compound. Molecular formulas, this is how we show which elements are present in a molecule or a compound. So for example, we have H2 is a molecule of hydrogen. C6H12O6 is a molecule of glucose. So the subscripts here mean there's two hydrogens. So for glucose, the C6 means there's 6 carbons, 12 hydrogens, and 6 oxygens. And then H2O, that's water, that has 2 hydrogens and 1 oxygen. All right, this is what we just explained.